welcome back to Biostat. We're going to do one more example of a two-factor ANOVA. This one's a little less biological than some of the other ones, but it will serve our purposes. So let's kind of look at this. So I've got a study that was conducted to see if there were significant differences for the salaries of certain engineering majors. There are two factors. Factor one is degree, either bachelor's or master's. And factor two is the engineering type, or engineering degree type, really. Biomedical, mechanical, or civil engineers. And the salaries in the data set are in units of thousands. So let's import that data set and take a look at it. So we got that one. It's actually going to have one of those longer-winded ones where you can download it from my Dropbox folder. Hit enter, and before we attach it, I'm going to look at make sure that the factors and everything are correct in here. That they're called factors and not numbers, and they shouldn't be because they're using letters instead of numbers. Usually with R, letters or words for descriptors are usually considered factors instead of numbers, so you don't have to worry about that as much with those. And so yes, the degree and the type are broken down in factors of 2 levels for the degree, bachelor's or master's, and 3 levels, bio, civil or mechanical, for the degree type, or engineering type, that is. And then our actual response variable here are the actual salaries of certain individuals. So let's attach that, and we'll take a look at that data set. So I'm going to attach E, which is what I'm calling this data set. And we'll go up here and let's check out this data set real quick. So we got the salaries here in thousands of dollars, so 91.5 thousand. We see the first one and so forth and so on. And then you got the degree type. There were 8 bachelors in the biomedical and 8 mechanical in the biomedical. And there were 8 people apparently are salaries collected for civils at bachelor's degree level, and 8 at master's. And so, and the same thing for mechanical, 8 bachelor's, 8 master's degree salaries were collected. So we got a total of 48 salaries in this data set. Okay. And so let's commence to doing our usual checks that we have to do to check our assumptions. So as usual, we're going to start out with our box plots. And I'm going to put my par MF row equals C12 to give me a 1x2 window for my images. And we're going to do plot. Again, salary, or sal in this case, is the variable name for the response variable, or the measurements. Then we got factor 1, which is degree, plus factor 2, type, plus degree times type, the interaction term. And since there were 3 levels, were the majority of the levels I had here, I chose colors 4 through 7. Again, you can do whatever you want there. And we take a look at them, and there's some outliers in the first degree in the bachelor's versus master's degrees. Those are pretty normal looking plots, with the exception of that one outlier, but if we ignore the outlier, they're fairly normal looking. Can't really tell whether there's one's going to be highly different than the other, or at least statistically significantly different than one another. And then for the type, there may be some significant difference here, but the boxes are overlapping, so it's hard to tell. Again, we won't really know until we get down to that point of the procedure. And those plots, those box plots for all of those look pretty good as well. The bio one looks a little right skewed, even if you ignore the outlier there. Because we don't know where all these salaries came from. They could have come from different states, and you know how salaries in bigger cities, sometimes in smaller cities, can differ quite drastically because of the cost of living. So we don't know where these came from. That would be nice to know, but we don't. So anyway, box plots look pretty good to me, not too shabby. So now we need to look at the residual plots here. And we need to build our full model ANOVA first. So let's do that. Full M equals AOV. And in that AOV, we're going to do sal tilde, so the response tilde the factor 1 degree plus factor 2, which is type, plus the interaction term, which is degree times type, and the data set, it likes for us to put that in there too, so it's going to be data equals E. So we built that. Now we can do our plots for our full model to get our residual versus fitted and QQ plots. So plot full M. What else do I need in there? C open parentheses 1 comma 2, so it gives me the first two plot types in the residual plots, because there's up to 4, remember, but we only really need the first 2. And then PCH equals 19 for my filled in dots, and then for color here I'm going to do color equals degree colon type. Okay, and that. So looking at the residual versus fitted plot, I don't see a clear-cut pattern here. They're not perfect by any means, the variation amongst the different vertical lines here of color, or points of color. I don't see a basic clear-cut pattern here going on. There's not that what I call cornucopia or horn-shaped, where they're really small on one end and then ballooning out on the other. There's no real clear-cut pattern there. The normal QQ plot also isn't terrible looking. It's a little wavy at the bottom for me, but not bad enough that I would say that this is not normal. This is okay. It's a pretty good looking plot. It's not a hooker. We also need to do Levine's test, and don't forget, if you haven't already called it forth, you have to call forth library car, and it loaded the required package. Now we can run the Levine test, and in that we're going to put sal, so the response value tilde, and remember, we don't have to put in the full formula like we did in the full model ANOVA. We just need the interaction term, the degree times type. All right, so degree times type here, and then we need to tell it that we are doing data equals E here for the engineering data set, and then lastly we need to tell it center equals mean. What did it not like? Oh, I didn't spell Levine test correctly. I forgot an E in there. All right, now we're good. So it's p-value there is 2.2183, so that's large enough that we're not going to reject the null hypothesis of equal variance, and we're going to assume that the variances are equal. So the residual plot's kind of backed up on my assumption there, so I'm good to go. Now we can actually do the hypothesis test here. All right. What I would probably say there about that test is the following about the Levine test output. Be the following. Let me just pop it up here on the screen. I'd probably say since p is greater than 0.10, we can assume the variances are equal across the groups. This backs up what the residual versus fitted plot was showing us, and we can proceed to run the full model ANOVA to check for any significant interaction. Alright, so that's what we're going to do next. I'm going to sweep this out so we can start from the top. And so I need to state my hypotheses first, and for this, the test for interaction, we do For the full model ANOVA, we do HO, the degree and engineering type do not interact, and the HA is that the degree and engineering type do interact. Alright, so those are our HO and HA. So then we need to run the summary on the full model that we pulled in before. Since we already stated that, we don't have to type that in again. And the ANOVA table I get from that is this. And remember, when we're doing the full model ANOVA, we only care about the p-value from the interaction term, the degree colon type here. And so since that's way bigger than 0.10, we're not going to reject the null hypothesis here. We're going to assume that the two factors do not interact. Therefore, we can take them apart and look at them separately without having to be concerned about one or the other. So we can look at engineering type separate from degree, which is good. That makes things a little easier for us. And so the hypothesis or conclusion I would write here would be the following. Since p is greater than 0.05, we do not reject HO. There is no interaction between the degree and engineering type factors. Okay. I know I said 0.10 earlier. I meant to say 0.05. All right. So now probably need to back this up by doing the interaction plot just to take a look at it, and also to get some practice at it. And so remember, you can do this in two different ways, and one way usually will look a little better than others, but in this case, since the interaction p-value is so high, it probably wouldn't matter which direction you went. This one, first one I'm going to do is degree for factor A, and then enter in factor B the second, and then remember the measurement goes third, and everything else pretty much remains the same. I have to put my X label as whatever my first input was to match. Y label is salary to match the actual measurement variable or the response variable, salary. And then everything else can pretty much remain the same, and you may want to change the title there from what I've titled mine. But we're going to do this two different ways, so we're going to do it that way first. And as you can see, those lines aren't exactly parallel, but they're roughly parallel. They're not crossing over each other, and so they kind of back up the fact that we have no interaction. It's not perfect, but it could be a heck of a lot worse than it is. I wouldn't even call that ignorable. I'd call those roughly parallel, very roughly parallel. And if I ran the other version where I switched degree and type around, I just flip-flop to the places they are the first two entries. Let's see what that looks like. Should kind of look similar, with the fact that it'll look different, but I'm talking about the parallelness being roughly parallel. It should look very similar. So notice all I did was take and switch degree and type around here from what I did before. Oh, come on, keep. Alright, so degree and type, I just flip those around. Everything else pretty much remains the same, and the only thing I had to change there was type. If you want to do both of these at one time, that's okay too. And again, look at that. You get the two lines there represent the degrees of the degree level, which is master's or bachelor's, and the degree type or engineering degree type is represented along the bottom there. So each one of these dots represents the change in the mean for biomedical, civil, and mechanical engineers. Okay, and so they're still pretty roughly parallel. I mean, they're not perfect, but they're not changing direction either, so that's good. Okay, so being the fact that we see no interaction, we can switch over to the additive model. Now, if you look here before I run the additive model, you'll notice that the p-values for degree and p-values for type are both significant. They're both smaller than 0.05, so we have some strong evidence already. Let's see what happens to those values when we switch to the additive model. In other words, we pull out that interaction term. So if I create the additive model, add m, I'm doing ANOVA again. This time I'm going to do the salary, tilde, the degree, plus the type, and that's all I need. I don't need the plus the degree times type here. And I'm going to add in, let's see, I think it's data equals E. All right, and then we need to do the summary of that additive model. You could do all this in one step if you wanted to. It doesn't really matter. You just have to put the AOV, all that stuff in one place. That just calling it add-in makes it easier for us to do the multi-comparisons later as well. So that's why I usually name it something like add-m for additive model. And we put add-m in there, and we get our ANOVA table. Bring that up a little bit, and we'll notice here that the p-values didn't change much, but they got a little bit smaller when we removed that interaction term, which is having a little bit stronger case is always a good thing, and it's actually how you should do this. So looking at those, we have to do our hypothesis test on each one of those separately. So if we look at the degree factors for the main effects, degree, and then engineering type. If I do degree types, I'm going to do the following thing. All right. Degree factor, main effect. The null hypothesis here is that the mean of the bachelor's group, which is what tau sub beta stands for, the mean of the bachelor's group equals the mean of the master's degree group, and the HA is at least one of the mean salaries differs among the degree types. So the conclusion here, since 0.02 is 3.5 is between 0.001 and 0.05, we will reject the null hypothesis. There is strong evidence to conclude that the mean salaries differ among the degree types. All right, so we did find something relevant there. Similarly for the engineering type, all right, that p-value is 0.0167. It is also between 0.001 and 0.05. And so the HO here is that all the means for biomedical, civil, and mechanical are all equal, and the HA here is at least one of the mean salaries differs among the engineering types. And since that p-value was between 0.001 and 0.05, we'll reject the null hypothesis again here and say there is strong evidence to suggest that the mean salaries differ among the engineering types. Again, just to kind of reiterate this, you may not always find that both of these things are significant. If one of them happens to be marginal, it might not make any sense to go forth with doing it's okay to do the hypothesis tests here and write these things up saying whether they were significant or not, but when you find marginal evidence in one of these and you try to do multiple comparisons on them, sometimes you'll find that those are not, that you'll get none of your confidence intervals will be highly significant. They might even, some of them be marginal, or all have zero held within them. Matter of fact, we're about to run the Tukey's HSD on both of these main effects, degree and type, and we'll see what happens with that. We'll find out where our true differences really lie. So this is really the last step in this process. So we're going to do Tukey's HSD on the additive model information we built already on the degree type only. So it's Tukey's HSD. First input is additive model, or the add-m, which is why it's convenient that we built that earlier before we got the ANOVA summary table. And then degree in quotes. It could be in double quotes as well. And when you run that, we only get one confidence interval because we only had two groups down here. So we should only get one confidence interval. And it's significant. And both values are positive. So it means that the master's degree people had made more money on average than the bachelor's degree people did. And so we would interpret that particular confidence interval as such. At the 95% confidence level, the mean salaries for the engineers who had master's degrees were larger than those with bachelor's degrees by at least 1.7 and at most $21.8 thousand. So pretty simple, straightforward. That one's not too bad. Now, the bio, civil, and mechanical, we had 3 levels for that, if you look back at our interaction plot. So we'll get at most 3 confidence intervals, but they may not all be significant. So let's check that out. So for degree type or engineering type, we do the same Tukey's HSD, but we do add M and just type. All right. And when we run that, we get the following. We look at the p-values first to see, all right, there's a significant one. That's between 0.05 and 0.001, and the other 2 are rather large, or they're both greater than 0.10, so we don't have to deal with those. Plus, if we look at the values, we go from negative 21.1 to 8.5 here, and here we go from negative 3 to 26.6 here. Since there 0 fits in those intervals, those are inconsequential, means that mechanical and bio have no real difference between them, so we don't need to interpret that. And the mechanical and civil engineers have no real difference between those. But the first one is significant, and it goes from negative 32.9 to negative 3.23. And that's the civil versus the bio, and since they're both negative, that means that the biomedical engineers made more money on average than the civil engineers. And so we might interpret that interval as follows. At the 95% confidence level, the mean salaries for the biomedical engineers were larger than the civil engineers by at least 3.2 and at most $32.9 thousand. Notice the direction I did those in. All right. Drop the negative and go from smallest to largest. And that's pretty much it, folks. That's that in a nutshell. I know I went through this one a little bit quicker than I did the other one, but that's not a big deal. So if you have any questions about these, feel free to email me or join me on my office hours or on the Q&A sessions. And I hope everybody's doing well, and talk to you later.